My name is Mohamed Ahmed. I work at Siemens Energy. And in the last 7 years, I have been working a lot with time series data, mainly on time series forecasting use cases from research and from product development aspects. And what I basically would like to talk about today is the lessons that I have learned from my experience working with time series data for forecasting purposes. And also, the lessons are mainly for the transition that I made from kind of a research point of view into kind of like a product and productionalization point of view. So I'm going to start talking about basically introduction to time series forecasting to whomever do not know about them, just what's time series data and what's forecasting. Then delving into some applications and business impact of time series forecasting. Then I'm going to talk about basically the main topic, which is the lessons that I have learned. And then we can close and have some questions and discussion with you guys. So starting with time series data is basically a data that have kind of like a time signature. So it's ordered in a timely manner. And most likely all of you have been working or dealing or analyzing time series data on your day-to-day basis. Stock market data, sales data, weather data, all these are time series data because it's ordered in a timely manner. When it comes to the sources of time series data, as I said, it's almost in our day-to-day life, in everything that we work with, from weather to sales, stocks, IoT, if you are working in some companies have some assets or machines, social media and traffic, all these kind of sources provide us with time series data. When we talk about forecasting, we basically just want to predict the future of these time series data. When it comes to the stocks, you would like to know what would be the prices for tomorrow. When it comes to the weather, you want to know how it feels tomorrow. And it's very interesting because forecasting seems like kind of like a magic kind of world because no one knows the future. But actually, when it comes to the time series data, and especially because of the timely manner of its ordering, there is a lot that you can actually get from the historical data that helps you to predict the future. For many of the data sets that I have worked with, there is a lot of like inner and also external correlation in the data that enables you to predict the future values out of the historical data. So why forecasting? I mean, the business impact of forecasting is huge. I mean, since I started working, I have with time series data, I started working on the engineering world, like basically predicting, forecasting the future of signals, for example, for machines. But then I delved into sales world, into manufacturing and into supply chain, and I was amazed by the business impact that could have been made by time series forecasting. I mean, here is just some snippets of numbers or figures that I extracted from a McKinsey report in 2023 about the impacts of time series forecasting to different domains. You can see like 50% reduction in supply chain errors. I mean, that's a huge reduction in errors. Look at the reduction in lost sales, 65%, and many other interesting numbers. And these numbers could be turned into millions of euros, or of course billions of euros, depending on the size of the business. Here, this is also an interesting slide. So the slide basically shows the different potential AI use cases for different kinds of the business processes. But the stars that you can see here highlights the types of use cases that could actually benefit from time series forecasting. And it's really interesting because actually more than 50% of the AI use cases in general actually could benefit from time series forecasting. So they either could be based on time series forecasting or part of the solution could actually have a time series forecasting manner. Yeah, now I'm delving into the lessons learned, and I'm just going to use this kind of a journey through the how-to forecasting to talk about the lessons that I have learned. So, I mean, when it comes to the forecasting product development, it's similar to any other machine learning product development. Basically, it starts by collecting data, preparing data, developing a model, then putting it into production, and then continuously monitoring the model. And actually, the journey looks more like a circle than like a timeline or like a line, but I just made it like this just for storytelling purposes. And I said we're just gonna go over some lessons that I have learned throughout these steps of product development. Yeah, the first lesson basically in data collection is what everybody knows: garbage in, garbage out. Data quality is a very, very important aspect of any machine learning product development. Yeah, I'm just gonna here talk about the quality pillars, which is accuracy, completeness, and consistency. So your data has to be accurate in the sense that it should actually represent the physical phenomena that you're trying to represent. Complete. You don't have to have like unavailable data at some points in time. You don't have to have like missing data points. Consistency. The data should actually have the same meaning all over the history of its existence. And actually, from my experience, this is how my journey with the business actually looks like, is that they always fall under this confirmation bias, that basically they show you a sample data set that represents their understanding of the phenomena or of the problem that they're facing. And that's a problem because basically the sample data set basically looks like this dog, but the real data looks like that beast. Especially when it comes to these three pillars of the data. And from my experience, the thing that they mostly forget mentioning you about is that the completeness of the data. So they usually bring you a very nice data set that represents the phenomena, and then they ask you to build a forecasting model or build the features and the dependencies. But then you end up with, I mean, when you put it into production, you end up with a very, very interruptible workflows, just because the data actually in its source does not come in the right frequency, it's not available 100%, and many, many other issues. Yeah, another thing that I wanted to say is that AI can enhance data quality, but up to a point. I mean, what I just mentioned before is one of the things, is the confirmation bias thing. But other problems is actually kind of organizational sources, like data governance, for example. You could actually get a job to do kind of like a time series forecasting for a data set, but actually after you build a model and put it into production, it turns out that the data suddenly just disappears, and you don't know, for example, why, and then you just go around and ask, and then it turns out that, I don't know, they changed the source of this data to a completely other source. So having proper data governance in the organization and making sure that data assets have like this whole thing of like data stewards, data domain managers that actually guards them, make sure of their availability, their consistency, and other things. I also wanted to give examples about what AI can do and what AI can not do, or should do and should not do. So just here, I'm just going to give an example of a sensor. Let's say that this sensor measures the time of a machine, okay, of a lifetime or a lifetime of machine. And here, this sensor have 3 probes that put in different parts of the machine, and it measures, let's say, that the time of the machine using some thermodynamics principles or equations, and it came up with these kind of results. So different results according to different probes. You can use AI for this particular use case to have a very good like end results of better data quality, just because of the nature of the data. It's a very let's say that it's a data that's really understandable in the sense that the data should just go upwards, right? So if something is going downwards or stuck, then most likely it's wrong. But like sometimes you could actually try to use AI to clean data, but actually you try to over clean the data. So basically you try to take out some of the data that you think are outliers, but actually they're not. They have some meanings. This is an example of time series data that's measuring a phenomena, and what you notice here is that suddenly the time series data starts to have some outliers here. And if you use like AI to just clean the data with some assumptions that this is an outlier, then you're going to miss a very bad phenomena, which is that the machine is actually going for an outage or for a problem. So making sure that you don't just blindly do data cleaning or over data cleaning, so that you miss these kind of phenomena, is a lesson that I have learned, let's say, the hard way. Moving forward to the next step, which is exploratory data analysis, and yeah, the first lesson is basically understanding the patterns in data. And the good thing with time series data, as I mentioned earlier, is that there is like a lot of inherent characteristics in the data itself that you can use to determine the future. For example, this is a very famous data set that has an upward trend, if you notice, but also kind of like a seasonality. So if you see here that this data could actually be split into 2 or 3 components. The first part could be a trend component. The second part could be a seasonal component, and then the noise or the rest of these. This is kind of like the ABCD or like 101 of understanding the pattern in data, but I just wanted to use it as an example to explain how important is this. But there is a lot of intricacies and a lot of technicalities about basically understanding the patterns in the data itself. The second thing, actually, when it comes to exploratory data analysis, is actually external dependencies or like multivariate relations. This is a very nice plot, at least for a data scientist. If you're not a data scientist, you might not get anything from it. But if you try to split this plot and look at the part to the left, you can see that there is a correlation between these 2 variables. And these variables are actually the electricity demand and the electricity price. I did this a couple of years ago. I was building a forecasting model for the electricity prices. And I was using basically inherent or internal characteristics. But then when I included the demand of the electricity as an external factor that I use for the forecasting model, I noticed this really nice correlation that could be used, at least for this part of the plot. And it helped a lot increasing the accuracy of the model. So basically, understanding the data domain itself that you're working with will help you a lot, because basically knowing that, I mean, everybody knows that when the demand for the electricity increases, then the price most likely increases. So this is kind of like a domain knowledge that would really help you having a better forecasting accuracy. Sorry, going back to, going forward to model development, choosing a model. Before going forward, I wanted here to say that a very important lesson that I have learned in model selection is actually practicality. And by practicality here, I mean about like the organization that you work with and the tools that already exist. So one of the important things in product development is kind of reusability. And if you have something that works with a good accuracy, then it probably might be better to just reuse it instead of going for something new. Having said this, I mean, there is a lot of models that are created day by day. So probably today, maybe they have been kind of like a new time series forecasting model in the market or in the literature. And a lot of these models are having like really good accuracy. However, actually, I mean, even the classic models, okay, and the simple machine learning models do very well actually when it comes to accuracy. So what I learned is that if you have something that works, reusing it is the best thing to do, instead of just trying to go for something that's a state of the art. Because I mean, if it's a state of the art, this means most likely it's not stable yet, even if it has good accuracy, but its implementation might not be that stable, and then you will end up basically kind of working a lot in updating your code base every now and then. So as I said, these are kind of like the classic taxonomy of time series forecasting, classic models, autoregressive models, and exponential smoothing, and many, many other models here. Advanced models are machine learning-based models and deep learning models. But when we look at the state of the art, I mean, this is a paper that did kind of a survey to state of the art models, and it shows that, I hope that the colors here look clear to you, is that transformer-based models are like really kind of like one of the trendy models along with the MLP based models. And that makes sense because of how good transformers are. If you know large language models, that's basically transformers are the base for large language models, and that's why many of these models try to look into that area. This is also some results of applying these state-of-the-art models on many of the famous data sets and getting their results. Of course, transformer-based models do pretty well. And I wanted here to talk about foundational models, which is basically the large language models of time series forecasting. So models that are trained on a huge data set, and basically you just use them on new data sets. I mean, there is a lot of pros of these models. The first thing is that the zero-shot forecast. You don't have to train these models on your data. You just get them and then use them on your data set. Scalability. They could work on a big organizational level, and probably they should have good accuracy since they are trained on a huge amount of data. However, I mean, I think we are in a very early stage of having these foundational models in a very stable way because of these problems. I mean, of course, first high cost of training it because I mean, right now, unless one of the big companies try to do an effort to train kind of like a foundational model, then you have to do it yourself. Of course, there are some companies now, like I think Nixla and I think Luanties, I'm not sure, Hugging Face. They have some foundational models that they have trained on huge data sets, but still, there is not enough data sets, time series, enough data sets that enable us to say that, you know, this is like a really good foundational model that is the model to rule them, the one model to rule them all. I mean, data requirements, as said, we need data sets, huge data sets in order to train these models, and interpretability. I mean, they're not that far compared to the classic models in that sense. So, but we're looking forward to that. I mean, in our research part, we try to look into these areas. When it comes to having the model in production, I mean, deployment architecture, here we talk about practicalities. So make versus buy is something that I learned actually, is that as a data scientist, I feel very proud about my knowledge, and I would like to basically prove to my manager that I can do it. And you can actually do it. But actually, the company could just buy a solution that's way cheaper than what you and your team are doing. And I learned this particularly in the enterprise central tools. For example, if you're using, I don't know, SAP or Salesforce or each one of these tools. Now, many of these tools offer like out-of-the-box AI features, and some of these features are forecasting. And actually, we benchmarked many of our custom-built solutions against these, and I mean, there was not a huge difference. So if this is cheaper, just go for it. I mean, everybody knows that you can do it as a data scientist, but that's cheaper for the corporate. I mean, the second thing is new versus legacy architecture, and also this is the fight with the enterprise architects, because, I mean, they always like to leave things as they are, you know, and then you just come to them with like a very crazy, kind of like a new architecture of a solution, which, of course, it will work, but it's just going to mess up their work, and it's more practical probably to basically sometimes to adopt just the legacy architecture and frameworks of the company. And I was actually having a chat just before this talk with a friend who was basically mentioned this thing that they have like some legacy solutions, and the nature of their company prohibits them from going, for example, to cloud solutions or to these kind of things. So they have to host everything in their own data centers, and they have to use very specific frameworks and programming languages as well. So that's something that I also learned throughout the time. When it comes to monitoring performance, I wanted to talk here a bit about the characteristics of the data itself. So if we have a data set like this, and we build a model, let's say that this model classifies this data into, like, I don't know, this segment or this segment, and you imagine this line as basically the model, like the separator between the two kinds of data. I mean, one thing that could happen is that what is called virtual drift or data drift, that the characteristics of the data itself shifts or changes, but not to the point that changes the model itself. So you could still assume that the model fundamentally describes the data. However, the data characteristics shifts a bit. And for these kind of shifts, you could actually just build kind of like a retraining mechanism along with the workflow that you have. I mean, another kind of drift is the concept drift, which is that the actual phenomena that you're trying to predict or describe actually changes over time. Let's say in the very early picture that I showed about the relationship between demand and price. It could be that at one point, which actually I think happened during COVID time, that the correlation became very chaotic in the sense that you cannot actually rely on the correlation itself. So at that point in time, you need to actually reconsider the what we call feature engineering, like what exactly are the dependencies in the data or the characteristics in the data that you took as an assumption to build your model, and having this as well, like feature engineering as one of the steps in the retraining of the model could actually solve this problem. So basically you try to automatically do feature prioritization as part of the model development lifecycle itself. So yeah, I think I'm right in time actually to finish, but thanks a lot for attending the talk, and if you have any discussions, you can reach out to me.
Thank you so much, Mohamed. Thank you so much for an inspiring presentation. And we do have a few minutes for a couple of questions, if we have any from the audience. And I see one already in front here, so go ahead and ask your question.
Thank you. Time series forecasting is the best. I would like to hear your view on the foundational models and the accuracy. What is accuracy is sometimes a very domain-specific question. Over under forecasting, what type of metric do I use for accuracy? And I would like to hear your view on the foundational models and the accuracy and how that can be interpreted into different business problems. Do you see that will work well?
That's a very good question, and the answer is that I think it's completely dataset dependent. I mean, I have worked with many datasets where basically you could use, I don't know, like mean squared errors just to check the accuracy of the dataset, but then for some other datasets it doesn't make sense. You have to use another metric like root mean squared errors, or yeah. So it's completely dataset dependent, and when it comes to foundation models, and what I saw from the literature is that they try to use multiple metrics and try to project the average of how the foundational model is doing in each one of these. I think in the one that I showed here, the overview of the large language models, I think this is over here they're using multiple metrics to basically to gauge which one of the foundational models is better. But I agree with you, and I think that it's really tough to say that this foundation model is best for all kinds of data. It completely depends on the data set itself. So I think we're in an early stage to say that we have like a foundation model that could work for all kinds of data set. Thanks for the question.
Great, thank you for the question. Do we have another last one? Yeah, we can take you over here.
Thank you for an interesting talk. Granularity. Within physics, we typically say that you need a measurement that it's 10 times more accurate compared to the value you want to quantify. If you can, and you spoke a lot about outliers, which is important, of course, but if you could choose your granularity beforehand, what accuracy do you need compared to the prediction you make?
Accuracy in what exactly you mean? Sorry?
In the timestamp. So spaces between measurements. Do you want 1 second, 1 hour, 1 year? Why? What is your general rule for obtaining the correct granularity?
Data set dependent. I mean, I've worked with multiple data sets, and completely depending on how the characteristics of the data itself. To give you an example, I have been working with some machines data that measures some sensors out of the machine. And actually, I was using kind of like a 1 minute kind of granularity of that data to forecast some value in the future. But actually, when I looked at the characteristics of the data itself, it looked like it doesn't change that much on kind of like a daily basis. One example was that we wanted to do a forecasting for the machine's mileage data, like how the machine lifetime goes. And actually, I used 1 minute data, and then when I was talking with the engineers, they told me like, I mean, that doesn't make any sense. I mean, the machine usually, I mean, the life of the machine could be used on kind of like a daily basis. You just see how many hours was used yesterday. Why? Because they wanted to forecast for like a couple of years in the future. You cannot just forecast a couple of years in the future on a 1 minute kind of granularity. So it's use case dependent, but it's also kind of, it needs a domain knowledge as well. So as I showed in this example, I mean, the engineers that I work with, they gave me a kind of an insight about what would be a good granularity to the horizon that they're using.
Thank you.
Thanks.
It was such an honor to have you here. Thank you very much.
Thank you very much.
Thank you.